Imagine a simple, closed loop. It's a shape that seems so basic, yet it holds so much potential. It could be a circle, an oval, or any other smooth curve. It might even be a squiggly doodle, something irregular and free-form. Now, imagine placing 4 distinct points on this loop, anywhere you like. The question arises, can we always connect these points to form a rectangle, no matter where they are placed? This deceptively simple question opens a doorway into a world of fascinating mathematical shapes and concepts, inviting us to explore deeper. At first glance, the answer seems obvious. It feels like it should be straightforward. For many familiar shapes, it's easy to picture rectangles nestled within their boundaries, fitting neatly inside. But what if the loop takes on a more intricate form, with unexpected twists and turns? What if it twists and turns in ways that defy our initial expectations? The search for an answer leads us to explore the very nature of loops, points, and the spaces they inhabit, pushing the boundaries of our understanding. It's a journey that takes us from the familiar territory of two-dimensional geometry into the strange and wonderful realm of topology, where shapes and spaces behave in unexpected ways. Along the way, we encounter mind-bending objects like the Möbius strip and the Klein bottle, which challenge our conventional notions of geometry. These shapes challenge our intuition and reveal the hidden depths of mathematics, showing us that even the simplest questions can lead to profound discoveries. To tackle the rectangle problem, let's start with a key concept: midpoints. Imagine 2 points on our loop. The midpoint lies exactly halfway between them, dividing the loop's length into 2 equal parts. Now, consider the distance between 2 midpoints. As we move the original points around the loop, their midpoints shift as well, and the distance between these midpoints changes. This dance of distances holds the key to unlocking the rectangle mystery. If we can always find 2 pairs of points on the loop, whose midpoints are the same distance apart, then we can construct a rectangle. The sides of this rectangle will be the lines connecting the points in each pair, and the equal distances between the midpoints will ensure opposite sides are equal. To visualize this idea, let's represent each pair of points on our loop as a single point inside a square. The position of this new point within the square will correspond to the positions of the 2 original points on the loop. For example, if both original points are close together at the top of the loop, their corresponding point in the square will be near the top right corner. If the original points are far apart, one near the top and the other near the bottom, their representative point will be closer to the center of the square. By representing all possible pairs of points on the loop as points inside the square, we create a powerful tool for analyzing our rectangle problem. The square becomes a stage where the dance of points and distances unfolds, revealing hidden patterns and connections. Remember, we're dealing with pairs of points and the order doesn't matter. This is a fundamental concept in understanding the transformation we are about to explore. The pair, A, B, is the same as the pair, B, A. This symmetry is crucial as it simplifies our approach to visualizing complex shapes. This means that points in our square that are reflections across the diagonal represent the same pair of points on the loop. Essentially, we are identifying these points as equivalent. To simplify our visualization, we can glue these mirrored points together by folding the square along its diagonal. This folding operation helps us to see the connections more clearly. Imagine folding a piece of paper in half to create a triangle. This is the same idea. By doing this, we are effectively merging the mirrored points. The result of this folding is a surprising and fascinating shape: a Möbius strip. This shape is not just a theoretical construct, but can be created with a simple piece of paper. The Möbius strip is a one-sided surface with a single continuous edge. This unique property makes it a subject of great interest in both mathematics and art. If you were to trace your finger along its surface, you would eventually return to your starting point, having traveled both sides without ever lifting your finger. This continuous journey is what makes the Möbius strip so intriguing. This peculiar property is a direct consequence of our folding operation and the fact that we are dealing with unordered pairs of points. It beautifully illustrates how simple transformations can lead to complex and fascinating results. Section 5. Möbius strip, a one-sided wonder. The Möbius strip, with its single side and continuous edge, seems like an oddity, a mathematical curiosity. But its emergence from our rectangle problem hints at a deeper connection between seemingly simple questions and the profound concepts of topology. Topology, often called rubber sheet geometry, studies properties of shapes that remain unchanged under continuous deformations. Stretching, twisting, or bending a shape doesn't change its topological properties. Cutting or tearing, however, does. The Möbius strip is a prime example of a topological object. Its one-sidedness and single edge are properties that persist even if we twist or bend it. This inherent flexibility makes it a valuable tool for exploring the nature of surfaces and the spaces they inhabit. Section 6, from strip to bottle, the Klein bottle emerges. The Möbius strip, fascinating as it is just the beginning of our journey. By connecting the edges of the strip in a specific way, we can create an even more perplexing object. The Klein bottle. Imagine stretching the neck of the Möbius strip, bending it around and passing it through itself to connect with the opposite edge. This self-intersection is a defining characteristic of the Klein bottle, and it leads to some truly mind-bending properties. Like the Möbius strip, the Klein bottle has only one side. But unlike any surface we encounter in our everyday experience, it has no edges and no distinct inside or outside. It's a closed surface, meaning it's finite in extent, yet it encloses no volume. Section 7. Unraveling the mysteries of self-intersection. The self-intersection of the Klein bottle may seem like a mathematical sleight of hand, a trick of perspective. However, it highlights a crucial concept in topology, the difference between embedding and immersion. An embedding of a shape in a higher dimensional space means placing the shape within that space without any self-intersections. Think of a curve drawn on a flat sheet of paper. That's an embedding. An immersion, on the other hand, allows for self-intersections. The Klein bottle is a classic example of an immersion. It can't be embedded in three-dimensional space without intersecting itself, but it can be immersed in this space. This distinction between embedding and immersion is crucial for understanding the limitations of visualizing higher dimensional objects in lower dimensions. It also underscores the power of topology to reveal hidden relationships and properties that might not be apparent from a purely geometric perspective. Section 8. Smooth curves, rough curves, and the quest for inscribed rectangles. Returning to our original question about inscribed rectangles, the Möbius strip and the Klein bottle provide a surprising answer. It turns out that not all loops can accommodate an inscribed rectangle. If the loop is a smooth curve, like a circle or an ellipse, then we can always find an inscribed rectangle. However, if the loop is allowed to have sharp corners or cusps, then it might not be possible to inscribe a rectangle. This connection between the smoothness of a curve and the existence of an inscribed rectangle highlights the subtle interplay between geometry and topology. It also demonstrates how seemingly simple questions can lead to unexpected and profound mathematical insights. Section 9. Higher dimensions, a new perspective. The journey from loops to Möbius strips to Klein bottles has taken us to the edge of what we can visualize in 3 dimensions. But the story doesn't end there. Mathematicians have developed powerful tools and techniques for exploring these shapes in higher dimensions. By embedding the Klein bottle in a space with more than 3 dimensions, we can untie its self-intersection and visualize it without any overlaps. This higher dimensional perspective provides a richer understanding of its properties and its relationship to other topological objects. Exploring these shapes in higher dimensions is like putting on a new pair of glasses. Familiar objects take on new appearances and hidden patterns and connections are revealed. Section 10. The enduring allure of mathematical shapes. The journey into the world of Möbius strips, Klein bottles, and inscribed rectangles is a testament to the power of mathematical exploration. These shapes, with their unique properties, challenge our understanding of dimensions in space. It all started with a simple question: can we always inscribe a rectangle in a closed loop? This seemingly straightforward query opened up a world of complex and fascinating problems. The search for an answer led us to unexpected places, uncovering layers of mathematical beauty and complexity, revealing hidden connections between geometry, topology, and the nature of space itself. These connections show how intertwined different areas of mathematics can be. The beauty of mathematics lies not just in its ability to solve problems, but also in its capacity to inspire wonder and curiosity. It encourages us to look beyond the surface and explore the deeper truths. The Möbius strip and the Klein bottle, with their mind-bending properties, continue to captivate mathematicians and non-mathematicians alike, sparking endless discussions and explorations, reminding us that the universe of shapes and forms is far stranger and more wonderful than we might imagine. Each shape holds secrets waiting to be discovered. So, the next time you encounter a simple geometric shape, take a moment to ponder the hidden depths it might contain. Even the simplest shapes can lead to profound insights. You never know where a little mathematical curiosity might lead. It could be the start of a journey into the unknown, filled with wonder and discovery.